Okay, we have a problem on this week's homework that has to do with how many diagonals are there in a hexagon, an 11-gon, and an 18-gon. So let's go ahead and tackle question A, and perhaps on the way we can then answer 11 and 18 using what we discover from A. Now, perhaps the way you'd think to do this is simply to draw up a hexagon and count the diagonals, but I'm going to go ahead and start by trying to see if there's some sort of a pattern that I can apply to the hexagon's case that will also apply to the 11-gon and 18-gon's case. So I'm going to start out by just drawing up the most simple polygon that I can. That's a triangle, and count, if this is the number of sides, this would be the number of diagonals. So the number of sides here, of course, in this polygon is 3, and the number of diagonals, we can see that all the diagonals in this case, well, there are none. That if I connect any vertex to any other vertex, I actually get a side, so there are no diagonals here. So let's go ahead and now talk about what happens when we have quadrilaterals. So if we've got a 4-sided figure, then we've got, let's see, 4 sides, and the number of diagonals, if I sort of sketch them in here, I can see that I've got 2 diagonals there. Okay, well, let's try the 5-sided figure. So a 5-sided polygon, also known as a pentagon, would look something like this. 5 points, note 3 of which are collinear, and we connect all the points up, and we can see that there are 1, 2, 3, 4, 5 diagonals. So it looks like for the 5-sided figure there are, is that right? 5 diagonals. Let's see, 1, 2, 3, 4, 5, 6 diagonals. Sorry. 1, 2, 3, 4, 5. Oh, I'm sorry. I'm actually wrong. That should be 5. Okay, so let's go ahead and bump it up to the hexagon's case. So the hexagon, we have something like this drawn. I'm not going to make it a regular hexagon, but something with 6 sides. And now we can go ahead and draw in the diagonals. And what I'm starting to notice is that I really only need to draw up one vertex's set of diagonals, because I notice that I have 2 diagonals emanating from each of the vertices here. So in a sense, what I've got going on up here is 2 diagonals per vertex. And here what I'm going to have is 3 diagonals per vertex. So it looks like what would happen here is I would take each vertex, of which there are 6 of them, and I would multiply by 3. Since I have 3 diagonals per vertex, which would give me 18, which seems rather large compared to the 5 here. So let's go ahead and see if that worked here. If we have 2 diagonals per vertex, we would take the 5 vertices and multiply by 2. Oh, that's interesting, because I actually get something that's not equal to 5. So I actually have to divide this by 2 to make it equal to the 5 diagonals that I discovered just by inspection. And the question is, well, why did I have to divide by 2? And the answer to that question is the fact that every vertex has 2 diagonals emanating from it, but any one particular diagonal connects 2 vertices. So I would count it here, and I would count it there if I was counting diagonals when I do the 5 times 2. So I have to divide by 2 because I simply double counted every vertex when I say every vertex has 2 diagonals emanating from it. I've double counted every diagonal, I should say. So what I should probably do here is do 6 times 3 divided by 2, which would be 18 over 2, or just 9. And that seems to make sense, since I see this going up by 2. I see this one going up by 3. I would assume that this one then may go up by 4, which it appears to be doing. But let's go ahead and count them anyway. So I've got 1, 2, 3, 4, 5, 6, 7, 8, and I believe that's the last one at 9. So indeed, it seems like there are 9 vertices. And the general conclusion then that I would have, 9 would be the answer to question B. The hexagon has 9. But the general conclusion here is that this works for any number of sides. So if I have n sides, n-sided polygon, then what I need to do is take the number of sides, there's my n, right? And then what do I multiply by? I know I got to divide by 2. Well, it looks like it's just n minus 3 each of these places. So if this is n minus 3. If this is n, this is n minus 3. So it looks like it's n minus 3 divided by 2. So n times n minus 3 divided by 2. Let's just check to make sure that that's what was going on here with the square. N is 4, so it would be 4 times 4 minus 3 divided by 2. Let's see, 4 times 4 minus 3. 4 times 1 divided by 2 is 2. Indeed, it seems to be making sense. Up here, I would take n, which is 3, times 3 minus 3 divided by 2. Yep, sure enough, that seems to make sense there too. So I believe that we've got the correct formula here, which makes it fairly easy then to do part B, which is an 11gon. So n here is equal to 11. So we would have 11 times 11 minus 3 divided by 2, which would be equal to 11 times 8 divided by 2, which is equal to 44. And so, of course, we could certainly draw this up, but it would be sort of a nightmare to count all 44 diagonals. And then the last one is an 18gon. So let's see, if n is equal to 18, then the number of diagonals would be 18 times 18 minus 3 divided by 2, which is 18 times 15 divided by 2, which is the same as 9 times 15. What is 9 times 15? 45, 9, 135. Certainly wouldn't want to be counting all of those diagonals. So you can see how this incremental approach really helps you discover, the all-important piece, which of course is this equation, which relates the number of sides to the number of diagonals.